Hello everyone, today we're doing problem 9.52 and this question asks us to draw the substitution product formed with our starting material being 2R2-hexanol when it's treated with these following reagents in A, B, and C. So if we start off with A, we see that first we're treating our hexanol with sodium hydride. So remember, sodium hydride dissociates to Na plus and H minus. Na plus being your spectator ion, H minus being your hydride. H minus is very unstable, it'd rather be hydrogen gas, so it will abstract any labile protons. And one of the labile protons in this molecule is from our alcohol here. So it is now going to deprotonate our alcohol, making a formal negative oxygen bond, giving us our formal negative oxygen with hydrogen gas. And remember, when you make a bond, you break a bond. So the bond between the hydrogen and oxygen will break, giving those two electrons to the oxygen nucleus, giving us that formal negative charge. Now we have a negatively charged oxygen, which is very electronegative, very nucleophilic. So now we can use this as a nucleophile to attack any potential electrophiles. And in step 2, we introduce this nucleophile with an electrophile. So if you see here, we will use the lone pair electrons of oxygen to nucleophilically attack using SN2 mechanisms the electron poor carbon here, making a bond. When we make a bond, we break a bond. The bond that breaks is the bond that's bound to this very good leaving group, which is the halide iodine. And that gives us our final substitution product plus I minus. In B, we are reacting our alcohol with a tosyl chloride and pyridine. So if you remember, alcohols are very bad leaving groups. So they can potentially be nucleophiles, but they're a very bad leaving group. They cannot be a leaving group. So what a tosyl chloride does is convert your bad leaving group into something that is a very good leaving group, which can then be susceptible to a nucleophilic attack. So the reaction with our tosyl chloride makes our hydroxide into a very good leaving group, an O-tosylate, which makes this molecule a good electrophile, susceptible to nucleophilic attack. In step 2, we have this sodium methoxide, sodium being Na+, methoxide having the formal negative charge. Remember, this is a salt, dissociates in solution, sodium being a spectator ion, doesn't do anything, leaving us with a strong nucleophile. So now we have a strong nucleophile, and we can use those lone pair electrons on the oxygen nucleus to nucleophilically attack this electrophilic carbon, making a bond. When we make a bond, we break a bond. So remember, this is SN2 mechanism, 2 arrows, 1 step. It's a concerted mechanism. So we will get an inversion of stereochemistry around this chiral center. So because the tosylate was coming out as a wedge on the plane of the page, our nucleophile is going to attack from within the plane of the page, so represented by dashed lines. Remember, changing any 2 positions of substituents on a carbon will invert its stereochemistry. And because the hydroxide was going into the page, now we invert it, so it's coming out of the page now. Then we have this O-tosyl group. And we also have this sodium ion. Next, we are also making something similar to the second one. We're converting this hydroxide alcohol into a good leaving group with a reaction of PBr3. So this does a substitution from going to alcohol to a bromine halide. So remember, the bromine will attack this carbon using an SN2 mechanism. So right off the bat, we get that inversion of stereochemistry. So if you recall now, inversion stereochemistry will occur by changing the position of 2 substituents. So I'm just going to change around the hydroxide and proton, but the hydroxide gets converted to a good leaving group, which is bromine. Now we have an electrophilic molecule here, which can react with any nucleophiles we present, and the nucleophile we introduce is the methoxide group. The oxygen of methoxide will be used to attack this electrophilic carbon, making a bond. When you make a bond, you need to break a bond. The bond that breaks is this bromine ion, giving us our SN2 product. And remember, you get an inversion of stereochemistry when you do SN2 around chiral centers. So now we invert our stereochemistry to get our final product plus Br minus. The very last thing the question asks us to do is which of these three routes gives us the same products? So if you can see here, obviously the first one and the third one give us the same products. We have R rotation of this methoxide substituted group. However, the middle one is its enantiomer, meaning that if this is R rotation A and C, B is its S rotation with the same chemical formula. So this is what we call non-identical, non-superimposable mirror images of one another. So it's enantiomer.